There we go. Okay. All right. So, good morning, everybody. Welcome back to Math 115. So let me cast here and we will get started. Okay. So everybody should be able to see my screen here. And let me add a page in here so that I can put a couple of announcements on there. There's a couple of things I don't want you guys to forget about, which is, first of all, homework number 2 is due on Friday at 11:59 p.m. 59 p.m. And something you might want to know about that is I have office hours today. From 9:30 to 11:30. So if you have questions about the homework, or you've used up all except your last attempt on a homework problem, please come to office hours. I will help you work through it. I won't just give you the answer, but I will lead you down the right path, okay? So that's office hours. We also have exit slips due as usual, 1 week after each lecture day. For those of you that might have missed it last time, I have written out my skeleton notes in advance and posted them onto the Blackboard page. So if you go to the Blackboard page, you can either print these out or get them up on your tablet if you want to follow along with me as I kind of fill them out. Okay. Yeah, so I think that's all I have to say about that. So let's kind of recap where we were last time. Last time we were talking about functions. Okay, we learned what it means for something to be a function, and we drew some pretty pictures. We talked about function notation, and we talked about how we evaluate functions at points by plugging in with our parentheses. We tested some relations to find out if they were functions. Remember, that amounted to checking whether we had repeated inputs in the domain which were being mapped to different outputs in the range. Okay, if we had that happening, then it's not going to be a function. Okay, and the way we kind of parse that graphically is by using the vertical line test or the pencil test. Okay, so we can take these functions and we can pass our pencil kind of left and right over them. And if we see that they're going to cross the graph of our relation at more than one point, then we know that the relation has failed the vertical line test and cannot be a function. Okay, so we had 2 examples here of some parabolas. If we have an upwards facing parabola, it's okay. If we have a downwards facing, or if we have a sideways facing parabola, then it's going to fail our vertical line test because of there's those 2 red circles there. That's a problem. Okay, so that's where we were last time. And right at the end, we were kind of talking about domain some more. And we were talking about how to determine the domain when we're not just given a set of points, okay, for a relation, or when we're not just given like a table of values. But what if we actually just get the rule? Okay, if we're just given the function rule, the way we determine the domain, okay, is just by considering the largest set of real values for which the function has a sensible real valued output. Okay, so we want to think about all of the numbers which we can plug into something like, for this example, 1 over x minus 2. and get something sensible on the right-hand side. And for this one, there's really only one thing that we have to watch out for, which is we really don't want to do 1 divided by 0. This is bad. So let's hedge our bets by kind of saying, well, what's the only time when this is going to be 1 over 0? Well, that's going to happen if I plug in 2 for x, because then the bottom would be 2 minus 2. So we call the domain all real numbers except x equals 2. Okay? So there's one other thing that we kind of have to consider with domain here, and it has to do with usually with square roots, or really any even powered root. Okay, if we do any even power root, we can't do a even powered root of a negative number. Okay, we can, but we specified in our definition here up at the top, we want the output to be real valued. Okay, we could do a square root of a negative number, but we would get an imaginary number as an output. Okay, and we want a real number as an output. So in this case, we need x plus 7, the number which is under our square root, to be greater than or equal to 0. Okay, that's what we're going to need there. So we saw a couple lessons ago how we solved these inequalities. All we're going to do is just move that 7 over to the other side. And I'm just subtracting, so I don't need to worry about flipping the sign. We should have 7 there. Okay, so we just get x is larger than or equal to 7. And we can just call it a day there. We can just say that's our domain. Okay, all real numbers x which are larger than or equal to 7. Okay. I included, by the way, the equal to sign as well here, because we can do the square root of 7 minus 7. That would just be the square root of 0. And there are two numbers which we can multiply together to get 0. They're the numbers 0 and 0. Okay. Great. So let's try this one together. Okay. This one, I think we're going to need to combine both of our kind of two tricks here to find out what the domain of this function should be here. So we've got f of x is equal to 1 over the square root of x plus 1. Okay, 1 over the square root of x plus 1. So let's try this on our own. I'll give you guys a couple minutes to come up with some statements for the domain of this function here. After a couple minutes, we'll regroup. All right, let me ask, is there anybody out there who needs a little bit more time to work? Please raise your hand. Okay, seems like everybody's about done. All right, so who can help me with this problem here? Who can give me maybe a kind of concise way to write down the domain of this particular function? Any ideas? Hmm. You guys find this exercise challenging? Here's an answer coming in from Aeon. It says x should be larger than -1. Oh, by the way, I just realized I made a mistake up here on this top problem. This here, I should have subtracted 7 from both sides. X should be larger than or equal to -7. Please notice this negative sign here I just added above. Okay, I think Aeon's got it right on the money. It should be x is strictly larger than -1. Okay, and Aeon, maybe I can pick on you a little bit and ask you, why is it that you chose to use the strictly larger than sign and not the greater than or equal to sign? Can you put words to that? Exactly, very good. Okay, so 2 answers coming in from Omkamar and Aeon. They've got it right. We need to exclude the possibility of x equals to -1. Okay, so basically we have 2 rules here being combined. First of all, we need the square root of x plus 1 to be not equal to 0. Okay. We need that to be true, and we need x plus 1 to be a non-negative number. Okay, so if we solve these, we would get x should not be equal to -1, and x should be larger than or equal to -1. Okay. So the way we reconcile these two, if we want x to be not equal to -1 and x is greater than or equal to -1, the only numbers which will satisfy both of these properties will be the numbers which satisfy this property, x should be larger than -1. Okay. All right, so thanks for the participation, Ayan and Amkumar. All right, so there's two things really that we need to avoid when we're checking the domain. So it's even-powered roots of negative numbers and dividing by 0. So we should exclude from our domain any numbers which will result in the evaluation of our function requiring one of these two things. Okay, so those are the things that we want to avoid. Okay, so let's have one more example. We'll do this one together. So we have this function g of x, and it's equal to the square root of x squared plus 2x minus 3. Okay, and we want to know what is its domain. Well, I don't see any denominators, so I'm not really going to worry about our second rule, dividing by 0. Okay, but I am going to worry about my first rule because I do see an even-powered root. Okay, a square root here is an even-powered root, power is 2. And so I need to make sure that whatever I'm doing the square root of should be a non-negative number. Okay, it should be larger than or equal to 0. So what I want is for x squared plus 2x minus 3 to be larger than or equal to 0. Okay, this is what I want. Okay, so I know that this is a quadratic expression. Okay, and if I have a quadratic expression, I know it should look like a parabola. In fact, I even know that this parabola should open up because the coefficient on my squared term is positive 1. Okay, we discussed that a few times ago. So let's maybe graph it and see if we can get a better picture of what's going on. Okay, I think it's going to help us to graph this if we can factor this expression. I think we want to find two numbers which are going to multiply to negative 3 but sum to positive 2. I think those numbers are going to be x plus 1 and x, no, sorry, they should be x minus 1 and x plus 3. Okay. So we know that these two are the roots of this polynomial, okay? Or these are the factors of the polynomial. So we know that the roots will be x is equal to positive 1. That would make the left-hand factor 0. And x is equal to negative 3. So let's graph those on here. We have 1 and 1, 2, 3. So we know we have points here and here. Why don't I do it with another color? Here and here. Those are our roots. And we know it's an upwards facing parabola, so we know that it has to look like this. Okay. So that's what it would look like if we graphed it. And now if we want to find the x values for which our function takes values which are larger than 0, well, I just need to find all of the locations on the x-axis which result in my parabola lying above the x-axis or on it. Okay, so those are going to be the values where either x is larger than or equal to 1 or x is less than or equal to negative 3. Okay, so We don't like this middle section because in that area we have the value of our function is negative. But we do like these sections on the right and the left because in those areas the value of our function is going to be positive. Okay, so this was all to say that the domain of this function g of x is going to be the set of values for which this inner parabola x squared plus 2x minus 3 is going to take positive or possibly 0 as a value. Okay. So before we move on and talk about range, let me ask, are there any questions about domain and more specifically, maybe computing the domain when it's unspecified? So taking functions and trying to interpret the domain of the function just from the rule. Okay, well, don't forget, if you think of any questions, you can always ask after class or during office hours, which I have today from 9:30 to 11:30. Okay, so let's talk a little bit more about range now. Okay, now remember, we defined the range to be when we had our function, right, which was going from x into y, and we drew these circles, right, and we had some points in here, which were going to some points in y. We defined the range, okay, to be the subset of y, which gets mapped to by an element in x. Okay, so if we have all four of these guys going to just these 2 points here, then that's what we call the range. Okay, so remember the domain is all of the sets, all of the points which we can plug into our function. And the range is the set of points which is possible to come out the other side. Okay. So how do we interpret range when, again, we're not exactly given an explicit set of ordered pairs or a table of values? Okay. Let me move this. Okay. So we might have an example like the following. We have some function f of x equals x squared, and they tell us what the domain of the function is. They tell us the domain of the function is the set of values 3, 5, or is the set of values which are in between 3 and 5 inclusive. Okay. All right. So before we move on to part C and actually compute the range of f, let's just deal with these first 2 parts, which are a little bit more manageable, okay? We want to find out, is 10 in the range of f and is 4 in the range of f? Okay, and all we have to do in order to do this is check if f of x equals x squared equals 10, can we solve for an x value in our domain? So let's try it. All we have to do to solve this equation, x squared equals 10, is take the square root of both sides. Right? So we'll take x is equal to the square root of 10. Okay? Which is going to be equal to, I don't know, 3 point something. 3 point, I don't know. Let's try it. 3.16 something. 16 dot dot dot. Should write plus or minus. Plus or minus. Okay, so the question, can we solve for an x value, which is in this interval 3, 5 inclusive, is yes, we can, right? Because 3.16, positive 3.16 something, is going to be in this interval here, okay? If we drew it on a number line, we'd have like 3 and 5, and 3.16 would be inside our interval. We've got closed dots on each side, and it's overlapping, so we know we're good. So the answer to the question is yes, absolutely. 10 is in the range of f. Okay, so let's try to answer the same question for the number 4 here. Okay, so if we do that, all we have to do is check if we have x squared equals 4 and we solve for x, will that number be in between 3 and 5? Well, if we solve this, we would get x is equal to plus or minus 2. And remember, we needed to find an x value, which is in between these 2 points. But neither negative 2 nor positive 2 are going to be in our interval 3, 5. So our answer is no. 4 is not in the range of f. Okay? All right. So now for computing the actual range of f, okay, for computing the range of f, we need to make a slight observation, okay? And it's best to draw the graph of this thing in order to see that observation. Okay, so let's draw it. If we have f of x equals x squared, it's going to look like a parabola. And what I'm going to do now is I'm going to mark our domain on the x-axis. Okay? So we would have like 1, 2, 3, 4, 5. And our domain is from 3 to 5. So here's our domain. Okay? Now remember, these are the endpoints here. Our range is going to be the set of x value or set of y values, which are possibly given by points in the domain. Okay, so we're just going to look at this one section of the parabola between these two goalposts. Okay, and one observation that I need to make in order to find this range here is to recognize that as x increases from 3 to 5, our function is increasing. It's going up. okay? And it's a continuous function, meaning that I draw it without picking up my pencil. Okay, so the largest y value, which is going to possibly be given by the function f of x equals x squared on this interval, is going to be at the right-hand endpoint, right? This is where we're going to reach the highest y value. Okay, so the largest possible y value in the range will be 5. If we plug 5 into the equation, we would plug it like this, and we'd get 25. And then the smallest possible y value in the range is going to be given by the lowest point, which we can see just from looking at the graph, is going to occur on the left-hand side of our goalposts. Okay, we know that's the value where x is equal to 3, so we'll just plug 3 in, and we'll get 9. So the range of f is going to be given by 9, 25. I use the brackets here on 25 because I know there is a value 5, which is included in the domain, remember, such that 25 will get hit. Again, I include 9 for the same reason. And I wrote this as an interval because I can see that since this is a continuous function, I know that for any point, such as this brown one here, in the middle of the range, I know that I'm going to be able to find a point here, which is in between my 2 points there. Okay, we call that the intermediate value theorem. Okay, but you don't need to memorize that terminology. Okay, so these examples are getting a little bit more complex here. Let me pause and ask if anybody's confused by what I've done with this range stuff. Is there anything I could clarify a little bit better? Or any questions at all? Should we not worry about putting domain and range in interval form at the moment? I would say that you can express it in multiple ways. So for example, I could have expressed the range here as I could have said 9 should be less than or equal to x should be less than or equal to 25. Okay, or I could have said, well, not x actually, it should be y really, or f of x maybe. So I could have expressed it like this, or I could have said f of x takes values in the interval 9, 25. Okay, so you don't necessarily have to use interval notation, but what you can't do for a problem like this is make a table and say, you know, x and f of x and list all the possible points, right? Because you wouldn't be able to list them all because there's infinitely many of them. So we do need to make a statement that somehow captures, you know, infinitely many possible points in the domain and range in this case. So the way we would write that would be either by using interval notation or by using this kind of inequality notation here. Does that answer your question completely, Heidi? Okay, sweet. Another question coming in from Morgan. Will the range always be the squared values of the domain? The answer is no in general. The only reason that was true for our particular problem was because when we were given our initial example, we were given that f of x is going to be equal to x squared. So later on, we might have different functions like x squared over 3x plus 7 or something like that. We might have different function rules, okay? But if you're given that the function is f of x equals x squared, then yes, you're right. You could observe that any domain, you can just kind of square those values and you will get the range. But you're going to have to be a little bit careful about the order that you write it in, depending on if your domain is positive numbers or negative numbers or some mixture of the two. Okay, so overall, I think the way you're asking the question was just in general, is the range always going to be the square of the domain? And the answer is no. Sometimes the range will be much smaller or in an entirely different place or all real numbers for that matter. Is there any need to draw a graph always? No, not necessarily. You could have made this observation algebraically by using something which we're about to learn. Let's see, later on. We might not get to it today. So no, you could just recognize, say, by using a table. You could try some points like, I don't know, 3, 3.5, 4, 4.5, and 5, and you could plug these in and you'll recognize that these are going to be increasing as we move from left to right. So you could just kind of algebraically come to the conclusion that this is an increasing function, and that the kind of endpoints of our range are going to correspond to the endpoints of our domain being plugged into the function. But I think it's easier to see with the graph. I think if you can draw a graph, it will often help you. Okay, great questions from everyone. Is there anything else that is on someone's mind? Okay, then we can go ahead and move on and talk about how to interpret domain and range from a graph. So this is kind of following up on what Kumar was asking. If we have a graph such as this, and this is some function, I don't know, f of x. Okay, the way we read the domain and range from the graph is just by considering all of these points along this function. Okay, we consider all of these points. And we consider all of their possible x values, okay? So if I'm looking at the domain, all I have to do is draw these up here like this, and we can see that the domain is just going to be all of these numbers along the x-axis for which we could draw a vertical line and hit the graph of our function. Okay, so this is going to be our domain. Why don't I draw it like this? This is going to be our domain. Okay. And the range, likewise, is going to be the set of values on the y-axis, such that if I were to draw a horizontal line, I would then hit my function at some point. Okay, so those are going to be the values which lie in between this kind of minimum and maximum, okay, since we have a continuous function. Okay, so everything along here is going to be our range. This picture's getting a little bit cluttered at this point, but let's try to express this. We'll express the domain first using interval notation, or first using inequality notation, and then we'll express it in interval notation. So we know that the maximum x value here is going to be 4, it looks like. And the smallest possible x value for which we get a point, it looks like -1, 2, 3, 4, 5, 6, 7, 8. So our domain would be -8 is less than or equal to x is less than or equal to 4. Or x lies in the interval -8, 4. Okay, so that's how we would express the domain. And then for the range, remember the range deals with things in the vertical world. So we want to consider the set of values which f of x can take. Okay, and it looks like, well, it looks like if I had drawn this properly, this would go over to here. It looks like the smallest possible y value that I'm going to get is going to be -1, 2, 3, 4, 5 here. And the largest possible y value I would get would be 1, 2, 3, 4, 5, 6, all the way at the tippy top. So we would write -5 is less than or equal to f of x is less than or equal to, oh, is it 6? 6, yeah. Or you might write f of x lies in the interval -5, 6. Okay, so this is how we read domain and range from a graph. We just look for the set of x values such that if we were to draw a vertical line, we would hit the function at some point. And then we just, for the range, we just do the same thing, but we draw horizontal lines, and we look for all of the y values for which a horizontal line would intersect our graph at some point. Okay. Any questions about how we find the domain and range by looking at the graph of a function? All right, if not, we'll move on to probably the last thing we'll talk about for now. Maybe we'll have time to do the difference quotient. So the next thing I want to talk about is something called the average rate of change. And I find it kind of curious that they include average rate of change in this section, but they do. And so I'll do my best to describe it without really talking about calculus. So if we have a function, okay, such as the one that's drawn here, we call the average rate of change of this function f of x over the interval from a to b. So the interval here is, I'm talking about the domain going from a to b. What we call the average rate of change of this function over this interval is the slope of this line, which passes directly through a comma f of a and b comma f of b. So we call the average rate of change of f of x over this interval from a to b is the slope of the, quote, secant line, which is just a fancy way of saying a line which passes through those 2 points, which passes through the points a comma f of a and b comma f of b. Okay, and I guess the way that you could think about it would be as follows. Say that you're like a hiker, okay, on a hill, and you're hiking here, and you do this hike where you start at a comma f of a, and you end at b comma f of b. Okay, so you're moving in this direction. The average rate of change is going to be sort of like if I were to build a ramp into the wall, and sometimes it's a tunnel and sometimes it's a ramp. The question is, how quickly would the ramp have to rise in order for me to take like a direct path, which would go straight through the mountain at times and straight over the valleys at times, okay? So the question is, what should the slope of this ramp be? Okay. And the way that we compute it is just by computing the slope of this line. And we have 2 points on the line. So the way we compute the slope of a line which passes through 2 points is just by checking the rise over the run. And the total rise here was f of b minus f of a. And the total run was b minus a. So the average rate of change over this interval is going to be equal to f of b minus f of a divided by b minus a. Okay? All right, are there any questions about this particular topic? About computing average rate of change? Remember, this is just rise over run. Okay, well, if there are no questions, then we're done for today. Thank you for listening, and I'll see you next time. If you do have more questions, then stay after class. We can chat. I also have office hours from 9:30 to 11:30, so if you need homework help, hit me up. All right, have a great day, everybody. Yep, thanks, Heidi. You too. Yep, my pleasure.